So the title of this talk is Hosting Notebooks for 100,000 Users. You can find me on the internet at these various places. So I'm S. Sanderson on GitHub. I'm at Scott B. Sanderson on Twitter. I work at Quantopian, which we're going to talk about a little bit today. And so the outline for this talk is we're going to start with a demo of kind of the project that the rest of this talk is going to be about. So we have a sense of the system that we're building and how all these pieces fit together. And then I'm going to come back and talk about some of the goals and challenges that went into this project that I want to talk to you about. And in particular, I want to talk about this project kind of as a case study of all the different ways that Jupyter provides really interesting APIs for flexibly extending and modifying the core behavior of the Jupyter systems. And so in particular, I'm going to talk about how we manage user identity at Quantopian, how we've done some interesting things to facilitate notebook storage, how we deal with running multiple Jupyter Hub instances so that we can scale out to the number of users that we want to support, and finally the system that we've built for allowing people to share notebooks within our community. So with that, I'm just going to tab over to a quick demo here. So this is Quantopian. And what Quantopian is it's a community where people can come together online to develop and share and work on and learn about how to write quantitative trading strategies. So we provide a platform where people can write Python code in the browser to research and implement trading algorithms. So at the start of kind of the story of this talk, this was the core functionality we provided on the platform, which is this backtesting environment. So this is an environment where people could come and write trading strategies in Python and test them in the browser. And so this is kind of the simplest possible hello world algorithm on the platform, which is just to say at the start of every day, buy 10 shares of Apple. And so I can run that and see how it would have performed historically over time. And perhaps unsurprisingly, buying Apple in 2006 does pretty well. So that's great, right? So we had the start of this talk sort of around early 2014. We had this platform, we were pretty happy with it, and what we found is that we were getting a bunch of kind of strange feature requests from our users. So we were getting feature requests like, I want my trading algorithm to be able to plot data, or I want a debugger in the algorithm, not so that I can fix bugs, but so that I can stop and do an interactive analysis from inside my online trading algorithm. And to us, sort of initially, those seemed like kind of strange feature requests. Like we're listening to that and we were like, well, that's not really the point of the trading algorithms. Like the whole point is you want to automate this thing, not do stuff manually. And what we eventually sort of realized as a result of doing all of this is that people didn't actually want to do these things in their trading algorithms. And what they were telling us was that the hard part of writing a trading algorithm isn't writing the algorithm, right? It's not typing out the exact logic for how you want to place your trades. It's really about researching the ideas behind the algorithm, right? So it's about exploring and visualizing all the different kinds of financial data that we had available. It's about testing the hypotheses that go into your algorithm and building some sort of economic thesis about how the market works. And then it's about analyzing the results of those algorithms to try to understand what your algorithm is actually doing, right? So, all of this led us to think, well, how can we provide an environment where we can allow people to interactively explore all of the data that we had available on the platform so that they could better research the ideas that would ultimately make it into their trading algorithms? And the natural response for us, especially because we were built in Python, was Jupyter, right? This is sort of a classic use case for people to be able to pull up data, analyze data, visualize data, share those analyses with one another. Like Jupyter is really sort of a core, a great tool for solving that problem for us. So a couple of the goals that we had for sort of somehow bringing Jupyter into our platform. So one is we already had an existing web application, so we needed to figure out how are we going to integrate the Jupyter UI into this existing sort of large established code base. That was going to be an interesting challenge. Another one was we had at that time, and it's grown since then, but we had over 100,000 users using the site. So that means that sort of puts some different constraints on us that you might not have if you're running, a Jupyter server for a small research team or a lab where, maybe everyone goes out to lunch and you can reboot the servers and it's not that big of a deal. Like we have this big community, it's a really global community. So basically we need to be running 24/7 and we needed to figure out how we were going to support that. The other big thing is Quantopian has kind of always been first and foremost a community of people where they can come together and share ideas and work on ideas and collaborate on these ideas. And so we needed to figure out some story for how people could take the existing community workflows that they had and incorporate the notebook into that system as sort of a first-class citizen. So those are the sort of the things we wanted to get out of this. What are some of the challenges that come with that? So probably the first big obvious one is scale. So this goes across a couple dimensions. One of them is just we had a lot of users who want to be able to do things. And then maybe even more worrying is that the things that our users want to do are actually pretty resource intensive. So we expose, on the order of a couple hundred gigabytes at least of data on the platform. And the kinds of analyses that people want to do for these training algorithms are pretty resource intensive, right? They're RAM hungry, they're CPU hungry, they're doing things like training machine learning models, building very, very sophisticated statistical models of how the market works. So people need a fair amount of resources in order to do these kinds of analyses. And that more or less mandates that we needed to somehow spread our user base across a fairly large number of servers in order to support the workloads that we wanted to support. Sort of coming along for the ride with scale is reliability, right? So again, we're a public website. We've got users all over the globe. There's people on the site essentially 24/7. So we don't want to have things like downtime during releases. We want to be able to do rolling releases of the notebooks. Another thing is, when you're at a certain number of servers or at a certain level of scale, you should expect that your servers will crash for all kinds of horrifying reasons, right? So as a Quantopian user, you shouldn't lose your work if one of our servers has a hardware failure, say. And then finally, and sort of kind of uniquely for us, is we provide an open public platform for anyone on the internet to come and do these analyses. So we're essentially inviting strangers to come to our website and write arbitrary Python code on our servers. We need to be able to protect our users from one another, and so that either maliciously or more likely not maliciously, like people just write, runaway while loops, or they'll accidentally do all kinds of unpleasant things to themselves. And we want to make sure that when they do those things, it only happens to themselves and not to the other users on their server. So we needed some way to isolate users from one another. And so kind of the standard way that you usually solve these scale and reliability challenges is distribution, right? You make everything in your application stateless, you scale it horizontally, and you say, all right, I'm going to have some proxy sitting in front of my service, and whenever a request comes in or whatever some piece of work comes in, I'll delegate it out to the appropriate service or the appropriate server, and hopefully no one has to care. And so the problem with that for this is that Jupyter, in a whole bunch of ways, is kind of inherently stateful, right? So we edit and maintain these persistent documents where we're writing things and editing things and collaborating on things. We maintain and talk to these persistent kernel processes where you're sending code that maintains a live running sort of piece of state that you can interact with. So all these things kind of make it difficult for us to scale this in the way that we might scale a more traditional web service. And then one sort of particularly interesting piece of state that we often don't think about as state is user identity. So the standard Jupyter systems, at least at the time when we were building this, didn't really have a notion of user identity, and we had one at Quantopian, so we needed to figure out how to maintain that piece of state. So before I sort of dive into how we tried to solve some of those problems, I'm going to give you kind of a whirlwind tour of the architecture of some of the aspects of the Jupyter Notebook ecosystem. The goal of this isn't necessarily to make you an expert, but I'm hoping to get you enough information so that you can follow along for the parts of the talk that are going to be relevant. So there's two applications that are going to be relevant for this talk. One of them is the single user Jupyter server. So this is the thing when you type Jupyter space notebook in the terminal, this is the application that your browser is going to be connecting to. And so the basic way that this application works is there's a front end, which is composed of some HTML and some JavaScript that you connect to over the browser. And then when you execute a cell or you type a command or you do whatever it is that you do in Jupyter, it's going to talk to a running server that's running on your laptop, either over HTTPS or over a WebSocket connection. And that server has a bunch of responsibilities, but the important one for this talk is that the server spawns external processes called kernels, which are actually what execute your code. So when you open a notebook in your browser, the server spawns a kernel and then is responsible for making sure that when your browser sends a message saying, I want to execute this snippet of Python, the server routes that snippet of Python to the correct kernel, waits for the kernel to execute that code and return a response, and then routes all that information back and forth. So the server kind of acts as an intermediary between your browser and all these different kernels that are running. So that's great. One thing that doesn't have is a real notion of user identity, right? So the Jupyter Notebook, the vanilla notebook has a notion of authentication, right? You can have a password or you can have some way of saying, in order to log into the server, you need some secret. But the vanilla server doesn't really have a notion that I'm Scott and I have Scott's password and there's information that's specific to Scott. And so the application that was being built kind of around the same time that we were working on the system is an application called Jupyter Hub, which has since grown and become much more popular. And the hub essentially exists to solve the problem of how do we have a multi-user Jupyter Notebook server. And the hub is composed of three main pieces. So it has an authentication mechanism so that when you show up to the hub, it somehow can figure out that you are in fact you and route you to the appropriate server. It has a notion of spawners, which basically means that when you connect to the hub, it will make sure that you have a Jupyter Notebook server running somewhere that it can connect you to, and if necessary, it'll spawn a new server for you. And that notion is sort of configurable, so you can spawn a process or create a Docker container or put something off on your cluster or something like that, but it has this sort of general notion of spawning servers for your users. And then finally, the hub acts as a proxy. So you've authenticated, it spawns you a server, and then you can connect to the hub, and all of the users can connect to the hub. And what the hub will do is transparently route your connection to the appropriate server so that it presents the illusion that you're just talking to the notebook server, even though under the hood there's this layer of proxying happening. So just one more sort of diagram of that. These slides, by the way, are shamelessly stolen from Carol Willings' Jupyter Day Atlanta talk, because she's much better at diagrams than I am. So again, sort of the picture to have in mind here is you've got some set of people drawn in XKCD style here. They're all talking to this process called the configurable HTTP proxy. And the proxy communicates to the hub, which maintains the authentication stuff. And then it also routes messages to and from the server. So essentially every user here, they're all talking to the proxy, but then they're being routed to and from their appropriate Jupyter server. Cool, so you guys are all now experts on how all the Jupyter applications work. So with that kind of background in mind, I'm going to talk about how we tried to solve some of these problems. So the first problem I want to talk about is user identity. Right, so by default, Jupyter Hub has this notion of authentication, and what it does is it authenticates users via Unix username and password. So if you were going to SSH to a server, or you were just going to connect to it via terminal or something like that, you've got a username, you've got a password. So that's sort of bad news for us at Quantopian, because we don't really want to give Unix logins to 100,000 users, right? That seems like a recipe for sadness. The good news for us is that we do already have a login system, right? Quantopian has a login system, and you can log in and you have your Quantopian resources. So that's some good news. The even better news for us is that Jupyter Hub's authentication mechanism is pluggable. So Jupyter Hub defines this interface called an authenticator, and essentially it needs to be a class that implements a method called authenticate that takes data received from the browser and figures out, are you actually the user that you're claiming to be, and if so, what user are you? So the simplest thing you could imagine is just having sort of a file with usernames and passwords, or maybe a dictionary. But we can build a more complex authenticator using the same interface. So in particular, we use a system called OAuthenticator. And this uses a fairly well-established protocol called OAuth that allows some website that already has a notion of authentication to authenticate you on behalf of some other service. So if you've ever logged into some random service with Google or with Facebook or with Twitter, you're using OAuth to do that. And that site is using Facebook or Google or Twitter as an OAuth provider. And so what we did is we used high quality open source libraries to make the Quantopian front end an OAuth provider, and then use that to authenticate our users to our notebook system. The next problem I want to talk about is notebook storage. In a lot of ways, this is kind of the thorniest problem that we had to solve. And that's because it's so deeply tied with that state problem that I mentioned being this really hard problem. Right, so the normal Jupyter Notebook server provides this file system-like interface for storing notebooks, where I can navigate directories, and I can move around, and I can rename notebooks, and I can open notebooks, and it sort of presents the illusion that I have essentially a file system. That file system manipulation is abstracted behind an HTTP API called the Contents API. And essentially the way that the Contents API works is that it takes all of our sort of abstract file system operations like reading a notebook and loading a notebook and saving a notebook and deleting a notebook and translates them into HTTP verbs. So for example, if I want to load a notebook, I'll make a GET request to a given URL. If I want to save a notebook, I'll make a POST request. If I want to delete a notebook, I'll make a delete request. And there's a couple extra endpoints for doing things like saving and restoring checkpoints, but the core idea is basically we're mapping HTTP verbs to file system operations. This stuff all works with this sort of abstract models notion, which are just blobs of JSON that represent the content of a file plus some additional information. So here we've got the notebook that I'm actually modifying or operating on, plus some additional metadata like when it was created, what its name is, what its path is, whether or not it's writable. So the idea is that we can send these snippets of JSON back and forth and use them to represent the file system operations that we want to do. The Contents API in the standard notebook server is implemented by this interface called the Contents Manager. And the default is a fairly straightforward pass-through to the file system. And it's essentially what you'd expect, where if you make a GET request, it reads this corresponding file, sends you back the data. If you make a POST request, takes your data, writes it to the file system. And so the good news for us is that, like that authentication mechanism we saw before, this contents manager system is pluggable, or is configurable. So the interface for implementing a contents manager looks like this. It's a little bit more complicated than authentication, but not a whole lot more complicated. So we need to be able to get notebooks and save notebooks and delete notebooks and rename things and check if things exist. But essentially, you implement a class with 7 methods or so, and you can change what it means to do all these file system operations to whatever it is that you want to do. So we saw that, and we said, well, state is this really hard problem for us, especially if we want to be, spread out across multiple servers, because, if we're storing notebooks on the file system, then we either have to have some sort of network file system, or we have to be doing, saves and restores and loads, and, how do we handle like all kinds of unpleasant failures? Like that seemed like a really, really hard problem. And so we looked at that and we said, well, we're not very good at managing state, but we've had applications, since the 1960s that are really good at managing state, and they're called databases. So what if we take, databases and said, instead of us trying to solve the state problem, we're going to make that, PostgreSQL problem. And so what we did is we wrote a library called PGContents, which acts as a drop-in replacement for the existing file contents manager. So instead of storing our notebooks on disk on the file system, we store them in a Postgres database, and we use IPython's ability to configure the contents manager to sort of transparently swap out the notebook storage without actually having any sort of visible changes to our users. So I'm going to do a quick mini demo of PGContents. So here I've got a Jupyter Notebook server. And this, for all the world, looks like a normal, vanilla Jupyter Notebook server, and I can execute cells and run cells and, edit and modify and delete cells and do all the things that I, as a Jupyter Notebook user, love to do. And I can also, navigate directories and open notebooks, and I can have things in directories, right? All the things that I, as a Jupyter Notebook user, like to do. And so, that we might, that might not be that interesting to us, except if we look at the directory that I'm in here, we'll notice that those notebooks actually are nowhere to be found on the file system. And what we can see is that when I ran this notebook server, what I did was I ran Jupyter Notebook and I passed it a path to this config file. And if I open that up, example Jupyter, then we can see that I'm actually telling IPython to use a different contents manager class. So I'm saying use the Postgres contents manager as your contents manager class, and then I have to give it a little bit more additional information. So I have to, for example, give it a database URL to tell it this is where we should connect to Postgres for the notebook storage. I can also give it a user ID so that I can have separate namespaces for all these users, right? It would be unfortunate if only one user could have untitled.ipynb. That would very quickly become a bad situation. So we want to have separate namespaces for all those different users. And then there's a couple other more specific things. So things like setting a maximum file size so that someone doesn't try to put 100 gigabyte notebook into our database. And then, oops, there we go. And then the way that gets implemented is I can do, I can connect to my SQL terminal and do select star from pgcontents.files, right? And we can see that this is how my notebooks are actually stored. So I've got an ID and a name and a user ID and a parent. And these files are actually essentially stored as just binary blobs in the database. So that's PGContents. So it's actually fully API compatible with the default contents manager. The way that we test PGContents is we subclass the file contents manager's test suite, plug in our own class, and assert that we pass the exact same test suite. In addition to that, it provides a couple additional features. So it has separate namespaces per user. We support multiple checkpoints per notebook, which is a thing that the default file system implementation doesn't support. It supports a configurable maximum file size. And we also support optional encryption at rest via the cryptography package. So for us, we care quite a lot about sort of maintaining and protecting our users' IP. We want to make sure that if someone compromises our database, that they don't get access to their notebooks. And finally, it provides this ability to actually combine file system based in Postgres storage via sort of like a hybrid mounting system. So some fun vanity metrics, because everyone loves vanity metrics. We've had over 65,000 users who have created a notebook. These stats are as of August of last year, so these are actually a little bit out of date. We've got over 220,000 total notebooks. We've got 310,000 total checkpoints. And we've stored over 450 gigabytes of notebooks. And I would guess that these are probably 30 to 50% larger than this by now. So when we initially implemented this, we kind of weren't sure that this was going to work for us in the long term. We implement this and we were like, oh, it's kind of weird. We're storing these like giant binary blobs in a Postgres database. Like, is that really going to work? This has actually worked great for us. I've been very impressed with Postgres' ability to handle this load. It turns out that Postgres actually has this really awesome system called Toast, which I can never remember what it stands for, but it's a system for storing large binary blobs sort of outside of the normal tuple where it would store things. And then it makes it actually very capable of handling this workload with pretty heavy load. The most significant issue we ran into is running out of database connections. So when you have an open connection to a Postgres database, that consumes some amount of RAM on the database. And so if you have thousands of notebook connections open, your database yells at you. There's already great robust tooling for solving this problem. So in particular, there's a tool called PG Bouncer that does transparent connection pooling. So instead of connecting directly to the database, we can connect to PG Bouncer. PG Bouncer maintains a reasonable number of connections, and we can multiplex across those. So that's PG contents. The next problem that we wanted to solve is multiple hubs. And so to explain this, I'm going to make the observation that Jupyter projects, as they've evolved over time, are essentially a series of increasingly elaborate lies. So what do I mean by that? So what I mean by that is that the Jupyter projects all present the illusion of talking directly to a kernel, but we've added increasingly many layers of indirection as we've evolved over time. So for example, this is IPython. In the beginning we had IPython, and IPython was good, right? IPython mostly didn't lie to us. We typed things into the kernel, we typed things into a terminal. The terminal read the code that we provided, executed it, showed us a result. There's basically no magic happening here. But then as we've evolved over time, we've added more and more layers of indirection. So for example, we went to the Jupyter console, and the Jupyter console now puts a layer of indirection where now we have the terminal process that's reading from us, and then we have a kernel process that's in a separate process, and the terminal sends messages to and from that kernel processes and displays them to us. And what that means is that I can do things like have multiple terminals connected to the same kernel, or I can have a terminal connected to a kernel and then disconnect it and then reconnect back later to it. So we've decoupled the lifetime of my sort of front-end client from the kernel that's actually executing my code. When we get to the Jupyter Notebook server, we add another layer of indirection. So now we're not even talking to a terminal anymore. Now we're talking to a browser, which is talking to a server, which is talking to a kernel, which is then sort of routing the messages all the way back and forth. So we're getting increasingly far away from our code, but we're still being presented with the illusion that we're just talking to a kernel. Jupyter Hub adds another layer of indirection here. So now we've got many users talking to many browsers, all talking to a proxy, which are talking to many servers, talking to many kernels, and messages are sort of flowing all the way back and forth. So at Quantopian, we didn't want to just have a single Jupyter Hub. We wanted to be able to scale robustly and have them go away and have that not fail. But we wanted to present the illusion of only having a single server. So, right, I said I want the illusion of having a single hub, but with multiple real hubs. Another thing we wanted to do was be able to embed the hub in an existing web page. And so we can kind of solve two birds with one stone by putting the hub in an iframe and having a system in our front end for deciding which hub to route a given user to. So we can maintain a mapping from users to the server that they're currently allocated to, and then keep track of which server you should get routed to dynamically, and use that to make sure that you get sent to the same place. So this is kind of the picture of that. So now we've got users talking to browsers, talking to Quantopian, which is then proxying across multiple hubs, which is proxying across multiple servers. It's going all the way back to the kernel, and messages are sort of flowing all the way back through. I'm going to skip this slide because I'm running out of time. So just some implementation notes. We have an application that keeps track of who's allocated to what server. When we load our research environment, we ask it, hey, what server are you on? If you're not there, we make a server for you, and then everything's good. I'm going to skip this. So the last system I want to talk about today is sharing notebooks. Right, so I mentioned before that Quantopian is in a lot of ways, first and foremost, this community of authors and researchers. And so we really wanted people to be able to sort of share and discuss their findings and integrate that in a first-class way into the notebook. And notebooks are really like this ideal format for this, right? If we've got these just piles of financial data and we're trying to pour through them and understand how the markets work, the notebook is a really great format for us to be able to compile our research and put it into a format that I can share with somebody else. And so in order to facilitate that, we built a set of extensions that we can use to share notebooks to our community and then clone them back into our environment. And so there's two pieces to this. There's an NB extension, which is the Jupyter's interface for sort of adding arbitrary extensions or arbitrary changes to the front end of the server. So this is, you can write HTML and JavaScript and inject it into the notebook page and have that somehow change the visual display or the UI of the notebook. And then there's a server extension, which is the API for us that allows us to add Python code to the notebook server backend. So for our sharing application, we have both of these. These are often used in tandem. So our NB extension adds this share button to the cell and allows you to sort of configure a cell to use as a preview for someone to look at the notebook. And then our server extension adds new endpoints so that when you click that share button, we post your notebook to the server, and then that uploads it to S3. And then our forums know how to look in S3 for those locations and figure out where, how to find a notebook and display it to you. So just sort of some general notes on that workflow. So this NB extension plus server extension combination, makes it pretty easy to add essentially arbitrarily powerful new functionality to the notebook, right? If I can change the UI and I can change the backend, I could in principle just rewrite the whole application as extensions. At some point it becomes not worth it to do that, but I can add sort of as much arbitrarily powerful logic as I want. In general, the server-side APIs tend to be sort of more robust and stable. They've been around longer. They're specified around more sort of complete interfaces. So they tend to be a little bit more stable. And if you've heard a whole bunch about Jupyter Lab probably in the last couple weeks, one of the motivations behind Jupyter Lab has been to sort of stabilize those front-end APIs and create sort of a solid foundation for people to build more robust front-end extensions on in the future. So wrapping up, I think I've got about 2 minutes left. So a couple conclusions I want to leave you with. So one is that Jupyter applications are really these amazingly extensible and customizable things, right? We talked about, changing notebook storage, adding this sharing mechanism, changing how authentication works, and we did all this without any source changes in Jupyter itself. These are all just using sort of standard extension mechanisms. And there's actually a whole host of extensions that I didn't even have time to talk about. So we have built extensions for monitoring memory. We've built a library called QGrid that gives you sort of an interactive scrollable data frame widget. We've changed the completion logic. We've changed how kernels get restarted. We've changed stuff about how we spawn notebooks. The list goes on. And we've done all of this without any sort of source changes within the Jupyter repositories. Another conclusion I want to leave you with is that state is the enemy of robustness and scalability. Anytime you can take a stateful problem and make it somebody else's stateful problem, it makes your life a lot easier because then you can just sort of have your application work and not care about dealing with that state. And finally, Jupyter is built on a throne of lies, by which I mean that appropriate use of indirection allows us to build these complex applications while presenting sort of a simple interface and having each individual piece be relatively simple. With that, I want to thank a couple people. So, Brian Granger, Carol Willing, Kyle Kelly, Min Reagan Kelly, really the whole IPython Jupyter team, and then the whole Quantopian team in particular, some of the people who worked on this project with me, David Michaelitz, Karen Rubin, Tim Shaver, but the whole Quantopian team have chipped in at various points in time. And with that, I think I've got about 1 minute for questions.